Okay, we're still trying to identify a transformation that has occurred. So let's look at a similar triangle that was in the last example that we looked at together. If I look at triangle ABC as my pre-image again, and triangle A prime, B prime, C prime as my image, I can look at this and tell that it appears the original image has been flipped or reversed to make my new image. That makes me think this is a reflection. If it's a reflection, then there must be a line of reflection about which the original image flipped over to create the ending image. So let's identify where that line of reflection is. To do this, we need to join corresponding points with each other again. Let's say I looked first at B to B prime. I want to find the perpendicular bisector of that segment. Now, in trying to do so, point B is okay. Is that a lattice point? Point B prime is not. So this kind of poses some difficulty for me. So I might want to look at a different pair of corresponding points. When we're performing these transformations, they don't always result in a nice, neat lattice point. So I want to look for them before I do any unnecessary work with decimals or fractions. Let's go to C prime. And once again, C is at a lattice point, but C prime is not. And then let's study A to A prime. Now, A to A prime does look like it occurs at a lattice point. So let's see if we can identify the perpendicular bisector of this segment. In a rotation, I had to identify two perpendicular bisectors and see where those two crossed. In a reflection, I only have to identify one perpendicular bisector of one segment. All of the segments will have the same perpendicular bisector, and I'll verify that for you in a moment using this graphing software. But for now, let's count this one out as you would on your paper and your graph paper. Let's identify the midpoint of this segment. To get from A to A prime, I would have to go up 1, 2, 3, 4, 5 units, and to the right 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Up 5 and right 15. Now, if I'm looking for the midpoint, I need to half those, which is going to bring in decimals, but at least they're halfway points, 0.5 decimals. So I need to go right 2.5. It's half of 5. I'm sorry, up 2.5, and right 7.5. So we go up. Let me get my point tool here. 1, 2.5. Right 7.5. 1, 2, 3, 4, 5, 6, 7.5. Right there on my line. Let's plot it perfectly. Oh, let's just do that. That'll be fine. Okay, so we're at the point -2.5, 8.5. Okay, now the perpendicular slope to that is what I want to think of next. So let's reduce down 5/15 to be 1/3. And let's do the perpendicular slope to 1/3, because I know that's the same. Ooh. Sorry about that. 1/3. And the perpendicular slope would be the opposite reciprocal. So I would have a -3/1. Okay. So from my midpoint, I want to go down 3 and right 1. Let me get my point tool here. I'm at my halfway point. So down 1, 2, 3, right 1. It's going to put me right smack in the middle of that box. Let's join this guy here. And then that represents graphically my line of reflection. I need to write the equation of that line of reflection. To do so, let's identify the points where our line was. We know that our line went through the midpoint, which was negative 2.5, 8.5 as my coordinates. And from there, we had another point using our slope. That would be at 1.5, comma 5.5, negative 1.5, comma 5.5. Okay, so we want to write the equation of the line that passes through these 2 points. I'll need to use my slope formula, point slope formula, which calls for me to do y minus y1 is equal to m times x minus x1. So I'll do y minus, well, I need to find my slope first. I already know, actually, my slope is negative 3. Sorry about that. So I need to pick one of these points. It doesn't matter which one we pick. Let's go with the 8.5 one. So we'll point in where y is 8.5. So y minus 8.5 is equal to, my slope is negative 3, x minus negative 2.5, which gives me plus 2.5. Let's clean this up a little bit. Y minus 8.5 would equal negative 3x, and then 3 times 2.5 is 7.5. That's a negative 3, so that would be minus 7.5. I will add 8.5 to each side, which leaves me with my equation in slope-intercept form, which is negative 3x plus y equals negative 3x plus 1. Okay? And that means my slope was negative 3, and my line should have crossed at positive 1. We can see that mine does almost cross at positive 1. We just probably got a little off with our graphing of the points here. If we move that over just a hair, it's probably that point that we graphed. Yeah. Okay? Now, if we let our graphing software verify these steps for us, they will be perfectly accurate. Like if I want to kind of undo what I did here where I constructed the perpendicular and I constructed the midpoint, let's let our graphing software do that for us. We can find our midpoint, and then we can construct the line that passes through that midpoint and is perpendicular to that line. Our graphing software will do that for us. That's the line we just graphed that we can see it perfectly goes through the point 0, 1 on my y-axis. What I want to show you here, since we have the graphing software, is that had I done B and B prime, I would have come out with the same perpendicular bisector. We chose not to use BB prime because it was very, not at a lattice point, it would have been some messy work for us by hand. But using a technology such as this software, it's not so bad. I just constructed the midpoint of BB prime, and then I will find the line that's perpendicular to BB prime. And I can see that it landed in the exact same location as the perpendicular bisector of AA prime. And very quickly, we'll do that with CC prime as well. I connect C to C prime. I calculate the midpoint, and my software is doing this for me. I construct the perpendicular at the midpoint, and I see that it's the exact same line I've done for BB prime and AA prime. So it wouldn't have mattered which pair of corresponding points I connected initially. We just chose AA prime because they were at lattice points. And that is identifying a reflection. Thanks.